Hello, I'm Krish Modi, and we'll begin by introducing the lab environment. The maze underscore environment.py module creates a 20 cross 20 grid based world with 400 possible states. The agent starts in the top left corner, colored green, and must navigate to the bottom right goal, marked yellow. 10% of cells contain walls, shown in black, that the agent must learn to avoid. The reward structure incentivizes reaching the goal quickly while penalizing steps, void collisions, and invalid moves. This sparse reward signal makes the problem challenging and realistic for reinforcement learning research. Milestone 1 implements classic tabular queue learning. The queue table stores all 1600 state action combinations explicitly, allowing perfect memorization of value functions. We use temporal difference learning with a learning rate of 0.1 and discount factor 0.9. Exploration follows epsilon greedy with linear decay from 90% random action to 10% over 500 episodes. Our custom constraint adds randomness every fifth episode to maintain the diversity. The algorithm structure is straightforward: initialize queue table, train for 100 episodes using TD updates, then evaluate with greedy policy over 100 test episodes. The training process reveals three distinct learning phases. From episode 1 to 200, the agent explores randomly with high negative rewards, averaging minus 1294. The randomness is essential for discovering the state space. Episodes 200 to 500 show rapid improvement as the agent learns which actions lead towards the goal. Rewards improve from minus 404 to nearly zero. By episode 500, Epsilon reaches its minimum of 0.1, marking the transition to exploitation. From episode 600 to 1000, the agent refines its policy, achieving positive rewards and reducing path length from 69 to 44 steps. The learning curve demonstrates clear convergence with low variance in the final 400 episodes. The final results validate our Q-learning implementation. After 1000 training episodes, the agent achieves 100% success rate with an average of 38 steps to reach the goal. This represents highly efficient navigation given the maze complexity and 10% wall density. Notice the performance gap between training and evaluation. Training averages 44 steps with epsilon 0.1 exploration, while greedy evaluation achieves 38 steps. This six-step improvement demonstrates that residual exploration during training slightly suboptimal paths. The success metrics chart shows convergence by episode 600 with zero failures thereafter, confirming the policy has fully converged. Tabular Q-learning provides an excellent baseline, perfect for small discrete domains where exact memorization is computationally feasible.
Hello everyone. I'll be presenting milestone 2 of this project, which focuses on Q learning with historical data for maze navigation. So, what exactly is milestone 2? The core concept here is simple but powerful, using past experience to speed up learning. Looking at this comparison table, you can see the key differences. While milestone 1 learns from scratch with random initialization over 100 episodes, milestone 2 takes a smarter approach. It learns from demonstrations with intelligent initialization. It only needs 500 episodes to achieve the same results. The key benefit: we get a 50% reduction in training time while maintaining identical performance. This is the power of curriculum learning in action. Let me show you the environment we are working with. This is a 20 by 20 grid maze which gives us 400 possible states. The green square in the top left corner is our start position at coordinate 0, 0. The yellow square in the bottom right is our goal at position 19, 19. The black squares you see scattered throughout are walls placed randomly at 10% density. The agent needs to navigate around these obstacles. Our reward structure is straightforward. Plus 100 points for reaching the goal, minus 1 point per step to encourage efficiency, and minus 10 points for colliding with walls. So now let's break down the algorithm into three key steps. First, collect the historical data. We run the milestone 1 agent for 500 episodes and filter to keep only the successful ones, specifically episodes where the agent reaches the goal in less than 200 steps. This filtering is crucial for quality. We end up with 306 successful episodes, which gave us over 40,000 experience tuples to learn from. The step 2 is pre-training from the Q table. We initialize our Q table with small random values, then apply Q learning updates across all historical data. This is the magic step before any actual training begins. We already covered 347 states, which is 87% of the entire maze. Step 3 is self play training. Now we continue learning for just 500 episodes, but here's where it gets interesting. We use an adaptive learning rate. For states we seen in historical data, we use a higher learning rate of 0.15 to prioritize those proven paths. For new states, we use the standard 0.1. We also start with lower position of 0.5 instead of 0.9, because we can already exploit what we know from the historical data. Let's look at the specific parameters that make this work. This table compares milestone 1 and milestone 2 side by side. Training episodes drops from 1000 to 500 because pre-training reduces the need for extensive exploration. The initial epsilon is lowered from 0.9 to 0.5 to exploit that historical knowledge right away. The base learning rate stays at 0.1 for standard exploration, but milestone 2 adds a special historical alpha of 0.15 to prioritize those proven paths we learned from those demonstrations. So we collected 500 episodes to generate those demonstrations, and our filter threshold of less than 200 steps ensured we only learned from high quality trajectories. Let's look at our training results. So first, the historical data statistics. From 500 episodes collected, we had 306 successful episodes. That is a 61% success rate. These generated over 40,000 SARS tuples, which stands for state action reward next state. Most importantly, we initialized 347 unique states covering 87% of the maze before training even started. Now, looking at the training progression during the self play phase, we can see clear improvement. At episode 100, we are still struggling with an average reward of negative 239 and taking over 200 steps. But watch now, quickly this improves. By episode 300, we are almost breaking even with a negative 6 reward and only 76 steps. By episode 400, we have gone positive with the reward of 27. By episode 500, we are at 44 reward and just 47 steps on average. This rapid convergence is exactly what we wanted to see. The learning curve visualization really tells the story. We can see we start around negative 2000 reward, which represents initial exploration phase, even with our pre-training. The blue line shows the raw, noisy rewards from individual episodes. The darker lines are moving averages over different windows, like 10, 50, and 100 episodes. What's impressive is the steep upward trend. We rapidly converge from those negative rewards to the positive territory, and by episode 400, we've reached stable, optimal performance. The smooth convergence of these moving averages show that we are not just getting lucky, we are genuinely learning a robust policy. This four panel visualization gives us a comprehensive view of training dynamics. In the top left, episode rewards show that our rewards stabilizing in positive territory with 50 episode moving average smoothing out the noise. Top right shows episode lengths. This is key. We start taking many steps per episode, but this quickly decreases to around 47 steps, showing we are finding more efficient paths. The bottom left histogram is particularly interesting. This reward distribution shows we have a bimodal pattern. Some episodes still explore and fail, but increasingly we are clustering around positive rewards, indicating successful goal reaching behavior. And finally, bottom right shows success rate using a 100 episode sliding window. We can see it climbing steadily, hitting 100% success by around episode 400. After that, we maintain perfect performance through the end of training. This is exactly what we wanted to see: consistent, reliable maze solving. Now, let's directly compare milestone 1 and milestone 2. The overlay is really revealing. The blue line represents milestone 1 running for a full 1000 episodes, and the orange line is milestone 2 with only 500 episodes. The key observation here is milestone two's learning curve is much steeper. It converges faster and reaches similar rewards levels with half the training. You can see that the time milestone 2 finishes at episode 500, it's already at the same performance level that milestone 1 needs 600 700 episodes to achieve. So the 50 episode moving average makes it crystal clear. Historical data pre-training gives us a massive head start, and we reach optimal performance in half the time. So here are some final evaluation results from 100 test episodes for each milestone. Looking at this table, the results are striking. The success rate, both achieve 100%. Average steps to goal, both are at 38 steps. And the average reward, both are at 63. But the performance is, completely identical. But look at the last row: training episodes. Milestone 1 needed 1000 episodes, and milestone 2 only needed 500. That's a 50% reduction, highlighted in green. The key insight here is powerful. Milestone 2 achieves identical final performance with 50% fewer training episodes. The demonstration, the power of curriculum learning. By learning from demonstrations before engaging in self play, we dramatically improve training efficiency without sacrificing the solution. To summarize, milestone 2 demonstrates curriculum learning through historical data. We pre trained with 306 successful episodes covering 87% of the state space before even the training began. We achieved the same performance as milestone 1 with 50% fewer episodes, 500 instead of 1000. Our adaptive learning rates efficiently exploit known good paths while still exploring new areas. We ended up with 100% success rate and 38 steps average, identical to the baseline.
So, hello everyone, I'm Aditya Srivastav and I'm here to present the Mile 3 of our Lab 9 Deep Q Networks implementation. So, the implementation overview is that the milestone 3 replaces the tabular Q values with a neural network approximation using a deep Q network, which is a DQN. We used a framework which is PyTorch, a GPU accelerated machine learning framework. The loss incorporated was Huber loss for robust gradient optimization. Exploration, we had epsilon greedy with decay from zero point 0.9 to zero point 0.1 for 500 episodes. A replay buffer, an experienced replay of capacity 1000 and a batch size of 32. The target network was updated 10 episodes for stability. The DQN architecture. The input layer had 400 neurons, one hot encoded state. The hidden layer 1 had 64 neurons, a ReLU activation, and a dropout with probability of 0.3. The hidden layer 2 had 64 neurons and ReLU activation, and the output layer had 4 neurons with Q values for action. The optimizer used was Adam with a learning rate of 0.001. The hardware was CUDA-enabled GPU with CPU fallback. The training results on a 20x20 maze. Um, so we had 1,000 training episodes and reward convergence after episode 600. The average reward increased from 1761, which was a plus 47 from the previous experimentation, and the average steps decreased from 822. The evaluation results for 100 test episodes, we had a success rate of 100%, and average steps to goal was 40.27, and average reward for the deep Q network was 59.02. The learning dynamics and visualizations. The reward curve shows exploitation transition around of episode 500. Episode length decreases sharply, indicating improved navigation. And the reward distribution histogram concentrated on positive values by episode 1000. The success rate stabilizes at 100% beyond episode 600. So here you can see the learning curve for a 20x20 maze. This is the milestone 3 of DQN. So the performance comparison between a milestone 1, milestone 2, and milestone 3, we saw a success rate of 100%. The average steps were taken were around 40.27, and the average reward was 59.02, and the convergence episode was at 600 episode number. The observation was the DQN matches Qtable performance but requires more training time due to sample decorrelation. So analysis, a DQN versus Qtable. A DQN generalizes state action mapping through neural approximation. In small discrete domains like 400 states, tabular Q learning remains optimal. The DQN exhibits a 6% performance gap, which is 40.27 versus 38 steps. GPU acceleration offsets computational cost. Huber loss and target freezing stabilizes convergence. DQN's scalability advantage becomes evident for larger or continuous environments. Now, conclusion. The milestone 3 demonstrates successful transition from tabular to neural reinforcement learning. The key takeaways were that DQN achieves 100% rate with stable convergence, reinforces scalability for high-dimensional RL problems, and provides a foundation for future experiments involving policy gradients or action credit models. Thank you.
Okay, so let's go over the code and the live demo and the results a little bit. Um, so let's start with the maze underscore environment.py, which is the standard maze environment used in all three for consistency. The maze environment class creates a 20 cross 20 grid, a world with configurable wall density. If you can see, the reset method initializes each episode, placing the agent at position 00. The step function processes actions, 0 for up, 1 for down, 2 for left, 3 for right, and returns the next state, reward, and done flag. Wall collisions return -10 rewards and keep the agent in place. Then we can go over the visualize maze function generates a matplotlib plot to show in green, show the start in green, goal in yellow, and walls in black. And this modular design allows all three milestones to share identical maze configuration for a fair comparison. Now let's go over maze 1. So you can see we have taken maze environment as an import here, and this will be consistent in all three code files. So after running maze1.py, the results you can see here, uh, it trains tabular queue learning for 1000 episodes. Uh, Watch the console output. Rewards start at -1 to 94 with 656 steps, showing pure exploration. By episode 500, rewards approach to 0 as the agent learns efficient paths. Episode 1000 shows positive rewards and 44 average steps. The evaluation phase runs 100 greedy test episodes, achieving 100% success with 38 steps average. The program generates three plots, and you can see those three plots here that are also being used in the presentation earlier. So you have the initial maze in all three, or the initial maze are shown just to show that it is the same maze that all three models are trained on. Then we have the learning curve for milestone 1, and then we have the metrics for the panel to show how the training progress. And then the result is uh, saved using pickle to a pickle file for milestone 2 baseline comparison. Now let's go to maze 2. So milestone 2 begins by loading the milestone 1 pickle. It separately runs 500 episodes to collect historical data, which is our step, and it filters all the trajectories that takes less than 200 steps. So it counted it out and extracted and stored it in the buffer. The queue table pre-trains on this data, initializing 347 states before self-play begins. Self-play runs only 500 episodes with epsilon starting at zero point 0.5 instead of zero point 0.9. Final evolution matches milestone 1, which is 100% success with 38 steps. Now, if we go to the second result file, we have a training comparison between the two. And you can see that milestone 2 converges faster due to historical knowledge, while achieving the identical final performance as the first one. Now let's go to maze 3. Milestone 3 starts by detecting available hardware. In our case, you can see the CUDA version used, and it is my laptop's RTX 3060 GPU on which it is being trained on. The DQN creates a neural network with 400 input neurons, 264 neuron hidden layers with dropout, and 4 output Q values. Training runs for 1,000 episodes with experience replay, showing slower initial learning than uh, tabular methods, because rewards stay negative until episode 500. The final evolution achieves 100% success but requires 40.27 average steps, 6% more than tabular methods. The comparison plot shows all three approaches demonstrating the function approximation trade off. DQN sacrifices precision for the capability of being generalized. So that was the takeaway from the milestone 3. And here also you can see the comparison matrix, the comparison curve, and then you have the training metrics of the DQN method. Thank you.